we're going to do a reaction that's similar to oxymercuration, but it's like using mercury sulfate and water, right? And we're not going to go through the mechanisms for these because we already know, like, as far as the first step in each one, the addition of either boron or mercury, we already kind of have an idea of how that happens. All right, so when I do hydroboration on an alkyne, and this is my alkyne, when I do hydroboration on it, it's going to do the exact same thing that it would do if that was a double bond, and that is anti-Markovnikov addition of boron and hydrogen across that double bond. And then if I follow that up with hydrogen peroxide and sodium hydroxide, that boron, that boron intermediate, let me just draw it down here. So it's going to be this. Right, it's the same alkyl borane intermediate, or in this case, this would be a vinyl borane. All right, but just like with the alkene, I can add 2 more triple bonds to this and get 2 more vinyl boranes bonded to or 2 more vinyl groups bonded to boron, right? Because I got 2 hydrogens left on there. So this is a vinyl borane, right? So we know the outcome. We get anti-Markovnikov addition of H and OH. So the H is on the least substituted side. I'm sorry, the most substituted side, and the OH is on the least substituted side, and you can see that here. All right. So now what ends up happening is this thing actually rearranges, right? This won't stay like this. This is what we call an enol, right? The ene is for the alkene, the double bond, and the ol is for the alcohol. So the enol is unstable, right? So it actually rearranges. You can see the arrows here. This set of pair of electrons is coming here to make a pi bond between carbon and oxygen. And then this pair of electrons is coming here to put a lone pair on carbon. So there's a blank here, and we have to fill that in with what that intermediate is going to look like. So the ring doesn't change. That's not going anywhere. But for this carbon, now this becomes, let me just get the color part out of the way. Right, so that's positive, this is negative, and there's a hydrogen here too. Too many colors. I have to remember that next time. Right, so there's a hydrogen here, and then that carbon has a negative charge. Right, so now this is an intermediate, but this is what I get. Right, So how do I go from this intermediate to the aldehyde? What can I do? Right before, so look at what happened. Let's look at what happened. What changed going from this intermediate to the aldehyde? What's different?
Looks like the placement of the hydrogen that's attached to the oxygen transferred to the carbon,
Yes.
or the red carbon.
Yes. So this is actually what we call an intramolecular, and I'll explain that. Proton. I just talked about this in my other class too. Proton transfer, right? Intra simply means that it's happening within the same molecule, right? Inter would mean that there's something external that's reacting. Intramolecular means that it's happening in the same molecule.
Dr. Russell.
Yes.
Oh, you responded. Never mind.
Say again.
You responded to the message.
Okay, yeah. We good. All right. Am I missing something? Yeah, I'm missing a hydrogen. Nobody called me out. All right. So that intramolecular proton transfer is going to happen like this, right? And then that's going to get me to here. So this interconversion between the enol and the aldehyde, which is here, we call that tautomerism. Right? The specific definition is we call it keto enol tautomerism. Even though you're not always making a ketone in the as the final product, right? So the takeaway is this: if you do hydroboration followed by oxidation on a triple bond, you will not get an alcohol, right? You'll get an enol that rearranges to give you a carbonyl, right? And if it's anti-Markovnikov, then that carbonyl is going to end up on the least substituted carbon. If it's Markovnikov, it's going to end up on the most substituted carbon. So let's look at the mercury sulfide reaction, sulfate, I'm sorry, mercury sulfate reaction down below. All right, so I have my triple bond right here. That's my reactive species. I don't care anything about that ring. I don't care anything about anything else. It's the triple bond that's reacting, just like all the other reactions we learned on alkenes. It's the triple bond that's going to react. All right, so with this, it's going to follow the same well, not the same mechanism, but it's going to give you the same outcome as if you were doing oxymercuration on a double bond. So it's Markovnikov addition of water. So basically it's Markovnikov addition of H and OH. All right. So again, you see the OH on the most substituted carbon and the H that was added on the least substituted carbon. What's the name of this species again? It's called an enol. Just like up here. Same thing. It's an enol. Right? And then that is going to rearrange to give you this species. All right, now how do I get from here to the ketone that I'm going to make? Or how would let me not say that. What would the arrows look like for proton transfer if I want to take this proton and transfer it to carbon? What can I do?
Draw arrow from the hydrogen to the carbon.
You want to start the arrow here, like that?
Yeah.
Why is that problematic? I agree, there's got to be an arrow between them some kind of way, but why is that particular arrow problematic?
Oh, okay. We're taking it away from.
Remember, it's always source to sink, right? So
You would go from, would it go from the carbon to the hydrogen because that's a negative? So it's like attracting it to it?
Yes, so that's a source. When we talk about source to sink, this is something that's electron rich. Wrong, but come on, Russell, tighten up. This is a electron rich to something that's electron poor. That's always how electrons flow, from electron rich to something that's electron poor. So we would do this and then give these electrons back to oxygen. Right, so my product in this case is here. And this is a ketone. The whole process, actually, if we think about, if I only put this intermediate in with the electrons on carbon to show you what happens, because this actually is concerted, right? It's a concerted process, but I'm showing it stepwise so that you can get an idea of what's actually happening between the enol and the ketone form. All right, so we're gonna stick with this, but in reality, this all happens all at once. And again, this is what we call Tautomerism. I still remember when I was taking organic as an undergrad, and I was trying to teach myself this. It was like a Friday night. I don't know where I was. I was visiting with one of my friends or something. And I had my organic book and I was just pounding away at this, trying to figure out like how this rearrangement was happening. So yeah, it's weird teaching this and then remembering how I felt when I learned it. But anyway, no, we're not gonna take a trip down memory lane. All right. So let's go to number 2. Unless there are questions about the reactions up top. Again, we're not going through the mechanisms for those because we've seen the mechanism for hydroboration, oxidation. We've seen the mechanism for oxymercuration, and these follow similar pathways.
What is, I think I missed the part where you're talking about what an enol is exactly.
Yeah, so it's this intermediate. Like this is the product. This is the product of that first reaction, right? We know that if we take mercury sulfate and water and sulfuric acid, when we add that to a triple bond, not a double bond, a triple bond, it's going to give me the same thing that I would get if I added mercury acetate and water and sodium borohydride to a double bond. It's going to give me an alcohol, right? So this is and it's going to be Markovnikov addition, right? So the OHs ended up on the more substituted carbon, and then the hydrogen ending up on the least substituted carbon, which is what I have here. So that's an enol. It's a ene because it has a alkene, and it's an ol because it has an alcohol.
Okay, and then tautomerism is where you do the proton transfer?
Yeah, the tautomerism happens when the enol rearranges to give you a ketone or an aldehyde.
Okay, thank you.
Mm-hmm.
I have a question. Can you scroll back up to the first example? Okay.
All right, that's it. You just need to see it.
Yeah.
Okay, all right. All right, so let's work these two examples down here. What do I expect from this reaction, right? Don't worry about the final product. If I do hydroboration, oxidation on a triple bond, let's think about the enol first, and then we'll think about the final product. All right, so what can I expect from this? What would the product look like? Don't worry about the chain, that's just in there. We don't care about that because that's not going to react.
Do you have an alcohol on the least substituted carbon?
Yes. Right, because we're going to get the same thing here that we would get from an alkene. The only difference is now I'm working on an alkyne instead of an alkene. So this is going to be OH like that. And then this is H. And then there's another H here. All right. So this is the enol, but we just talked about this. The enol is not stable, so it's not going to remain an enol, right? You can actually rearrange this. So what would the aldehyde look like? Right? Or what would the carbonyl look like from this? Let me help you to understand this. All right. So if I'm going to make this into a carbonyl, I'm going to put a double bond here between these two carbons. All right. And then I'm going to have a single bond here to hydrogen, this hydrogen. And then this double bond is no longer going to exist. Right. That's what the rearrangement is going to do. It's going to take out the double bond between the carbons. It's going to add a hydrogen to the most substituted carbon in this case, and it's going to put a pi bond between the carbon and the oxygen where the alcohol is. So if I had to draw the final product, because that's what that is, right? It's because this is not going to stay like this. Right? This is only an intermediate form of what the final product is. If I had to draw the final product, it would look like this, where this is carbon, that's carbon. Like that, right? And this is again, I'm putting keto in quotes because that's actually an aldehyde. This is the keto form, and then this is the enol form, right? But if you can get to the enol, you should be able to get to the aldehyde or the keto form. All right, what about the second one? What is that going to look like?
Are you missing a hydrogen, another hydrogen on the carbon, on the other carbon to your left of the double bond?
Yes, I am. Thank you.
And you said it's keto because it's a ketone?
No, it's not a ketone. That's why I put keto in quotes. But it's a carbonyl.
Okay.
Right, but this is an aldehyde, so that's why I put keto in quotes because it's not really a ketone.
Okay, got it.
Yeah. All right. What about down here? Now my reagents are different. I'm using mercury sulfate, water, and sulfuric acid. So what do I get from that? Let's think about this, the enol form first. Where's the OH going? And where is the hydrogen going?
And then the substitute.
So with mercury is going to be Markovnikov addition, right? So this is coming here like this. And then the H is coming here. Like that. All right. So again, when this rearranges, it's going to rearrange to give you, right, a ketone. We're going to put a double bond here. We're going to lose this, and we're going to put another hydrogen here. This hydrogen, that's on the OH group. right? So that final product, because this is what it's going to end up as, and this is why it's difficult to convert alkynes into alcohols unless you take the triple bond all the way down to a single bond. It's very difficult to trap it as the enol unless you trap it with something where the OH gets converted into some other group. So this is going to be C. This is sloppy. Hold up. This is going to be C, double bond O, and then this carbon out here is going to become a CH3 like that. Anybody disagree with that? So to go from enol to the keto form, actually, I'm going to leave that because that's actually is a ketone. Right? Three things have to happen. I need a pi bond between carbon and oxygen. I need to lose the carbon-carbon pi bond, and I need to add a hydrogen to the other carbon where the carbon-carbon pi bond is, right? So those three things have to happen. But if you know the arrows, then you don't have to think about it like that, right? If you get to the enol, you could just simply rearrange it by doing this, right? You're gonna make a double bond here. You're gonna break that, and then that carbanion that's here, you're gonna take that and use it to pull off the proton from the OH group, right? So you need to get some reps with that. Yeah, a lot of reps with that. But those two reactions are only two reactions like this that we're going to look at. There are a ton of reactions that alkynes can do, but we're only going to focus on these two for the scope of what's going to be on the exam, right? And there's two other reactions that we're going to talk about, right? And they're in this reaction scheme down here, right? One of them is acetylide formation. You should have seen that in the video. And then the other is alkyne reduction. All right, so let's start out with the acetylide formation. So let me just copy this one reaction right here to explain this. Put this on a different page. Right, so with the acetylide, well, acetylene, which is this, that's another name for this particular alkyne is acetylene. We could take that and react it with a base and actually deprotonate or do proton transfer with the base with this proton. What's the pKa of that proton? If you watch the alkynes video.
Is it 25?
About 25. Good, excellent. So I need a strong base. I could use a strong base to pull it. That's not very acidic, but a strong enough base can rip that proton off, right? So I can take that and treat it with a base. I'm just going to use a generic base like this. All right, we've seen this before. This is acid-base chemistry. So this is nothing new, right? We've done this when we studied pKa. So that's why we don't have to spend an inordinate amount of time going back over how this happens because we already seen it, right? Actually, I'm not going to do that. I'm going to actually use the base that I have, right? So that's that. So I'm going to end up with this. Now I can use the sodium as a counter ion plus NH3, right? And then this is what we call an acetylide. anion, right? That acetylide anion is depending on what it attacks, what you reacted with, it's either going to be a nucleophile or it's going to be a base, but I want to focus on it being a nucleophile. I'm going to say can be. It can be a nucleophile or a base, right? It depends on what you reacted with. So in this case, we're going to react it with what's here. And that is, right, this benzyl iodide. So let me draw that out. So pH is an abbreviation for, remember our functional groups, this is an aromatic. Whenever you see pH, that's an abbreviation for that. All right, so pH is an abbreviation for the aromatic ring. So that reactant looks like this. So I'm just draw it. I'll draw it down here. All right, so this is pH, and then this is CH2. All right, because this vertex right here is a CH2. Everybody agree with that? That's a CH2?
Yes.
All right, so I'm going to take that and react it with my acetylide. So it's this, Russell, tighten up, plus this. Actually, let me turn it around. Make it easier to see. All right. And then my sodium is still hanging out here. All right. So now, what do you think is going to happen? This is again, this is something that we've seen before. This is not new. This is a nucleophile. This is an electrophile, right? This is a leaving group. What kind of reaction are we getting ready to do here? This was on the last test, by the way. Just in case you're thinking that you've never seen it before. Not this particular reaction, but this process. If I have a nucleophile in the presence of a leaving group, what normally happens there? Don't they just swap out?
Substitution.
It's a substitution reaction. Right? It's a substitution. So I'll have this nucleophile attacking. I'm going to change the color of my arrow so you can see it. It's going to attack here. Boom, like that. And I'm going to lose iodine. What type of substitution is that on that primary carbon? Wow.
Is it Sn2?
It's Sn. Thank you. Who was that?
Taj.
Taj Mahal. Thank you, brother. Thank you. It's a Sn2 substitution. It's a primary carbon. Remember, we talked about that in great detail. Primary carbons only do Sn2 substitution. When you're thinking about substitution in terms of is it Sn2 or Sn1, if it's a primary carbon, it can only do Sn2. All right. If you got that question right on the last exam, I'm going back and taking points off everybody except Taj. I'm joking. I had to say that quick because I'm gonna go tell the dean. He said he was gonna regrade our papers. I'm not gonna do that. But it's a Sn2 substitution. Like this is a great example of how everything we learned up to this point culminates and comes together, right? We're talking about nucleophiles and electrophiles. We're talking about leaving groups. We're talking about substitution. We're talking about acid-base chemistry and proton transfer. All of that is coming together in this one example, right? And we're talking about what the types of carbons, primary, secondary, tertiary. So this is a primary carbon, right? And this is Sn2 substitution. All right. The thing about the acetylide anion is that if it's attacking a primary carbon, it's going to do substitution. But if you have a secondary or a tertiary carbon, it's going to act as a base and do elimination. So like if this was, I'll write it down here. It's not a part of the example, but I might as well talk about it while we're here. So sometimes it'll do elimination, but the carbon has to be secondary or tertiary, right? So if I took a substrate similar to that one up top, but instead of it being primary, I added another carbon here, made it secondary, and then this is the proton right here, right? That acetylide would actually act as a base. So it would be this plus this. Right, it'll actually act as not that, I don't want that proton. Come on, boss, tighten up. It'll pull off one of these up here, one of the alpha protons. That red proton is not alpha. Alpha is always adjacent to the leaving group. And this is only in the case of the acetylide anion reacting with a secondary substrate. Actually gonna make that this one red, so you can see. Right. So if the acetylide is used in the presence of a secondary or tertiary carbon, right? This carbon right here is now secondary, where my leaving group is. Then it ends up doing elimination. But for that first step in the reaction up top, let's go back and put that in. Any questions about this before we go back and fill in that part?
Can you repeat what you just said about the I think it was the secondary carbon?
Yeah, if you use the acetylide, like up top, this was a primary.
Mm-hmm.
That's going to do substitution.
Right.
Down here is a secondary carbon where the leaving group is.
Okay.
That's going to do elimination.
Okay.
And it can be secondary or tertiary. I gave a way to remember that in that video. I think it was like 1 sausage and two or three eggs, something like that. Is that right?
Yeah.
So if it's
Yeah.
primary, it's going to do substitution. If it's secondary or tertiary, it's going to do elimination. So it's like 1 sausage or two or three eggs. That's what the way I gave you to remember that. Right, so 1S and 2, 3E. Primary is substitution, secondary, tertiary is elimination. All right, let's go back up to the example. So we have for product A, we can write that in now because we know what that looks like. It looks like this. Hydrogens in here. Right, that's the first thing that we get. So this is A. A is now a precursor to B or C, right? If you want to do, let's do C because C is easy to predict, very easy to predict, right? What are we going to get from C if we take the product from A, which is what that is, as my start material to form C? And I'm using the same set of reagents, right? I'm using sodium amide and ammonia, and then benzyl iodide. What am I going to get for B? I'm sorry, for C. What would that set of reagents do to this alkyne right here?
Would it attack that hydrogen
Yep.
and then like attach it?
Yep.
Like
So we're doing
attach
the
to it?
same reaction, but just doing it on the other side. Is that right?
Yeah.
Yep. So the product from that is going to be, I'm going to change, make it, I'll leave that red, and then I'll make the other side a different color. That's that. And then on the other side, I'm gonna have the same thing. Let me fix that up. Right, so I'm gonna get the same thing on the other side. It's the same set of reagents, right? Sodium amide and ammonia, and then that's gonna remove the hydrogen from the alkyne, and then I'm bringing in that electrophile, and it's just gonna react, that primary electrophile is gonna react with that. All right, so that's C. Anybody not see that? I'm starting out with A, and A is a precursor for C.
You said the pH is what forms that
The
aromatic.
ring, the aromatic ring, yes. Anytime you see this as this abbreviation, it means that there's an aromatic ring present. A benzene ring. All right, any questions about those two? All right, so how much time? We got 4 minutes left. Let's go ahead and do D. Let's figure out what's going to be for D. So this is the other set of reagents, right? All right, so I'm going to take this. This is a reduction method. Right, this is one way to convert an alkyne into an alkene. This is lithium followed by ammonia. All right, can somebody tell me what type of alkene this will give you if you watch the
Trans.
It would give you a very good, a trans alkene, right? So the product of the product is going to be a trans alkene. Excellent. Who was that?
Yeah.
Nice work. Nice work. Nice work. Nice work. So for C, we know what C is, right? C looks like, I gotta erase this because I got it somewhere else anyway. So C looks like this. Let me draw it in. So this is, and I'm just gonna keep it all the same color. So that's that on one side, and then on the other side like this. All right, we're okay with that? Whenever you see an alkyne like this, don't panic. There's a carbon here and a carbon here, right? And then there's a carbon at each one of these vertices too, so don't panic. All right, so I want to turn this, I want to treat this with lithium. This is C. We already said that down here. That's what we made when we took the product from the first reaction, which is A, and then treated it with a base followed by an electrophile, right? This is what we got. Okay, so now I want to take this and turn it into a trans alkene because the lithium and ammonia is going to give me a trans alkene. It's going to take that alkene and make it into a trans double bond. The alkyne, I'm sorry, and make it into a trans double bond. How would I show that? What would that look like? What does trans mean in terms of a double bond?
It's opposite.
Opposite sides. So I can put my double bond in for D, like so. Is that right? And then on this side, sorry, on this side it's going to be here. Dang it. Hold up, let me fix that. Right now, the other group, is it going to be here or is it going to be here?
It's at the bottom.
The bottom, right? It's a trans alkene, so that means that the substituents on the alkene are opposite to one another. So I'm going to draw that down here. Right. So this is my trans alkene. Lithium and ammonia in the presence of an alkyne is going to take that alkyne down to the alkene, but the alkene you get is going to be trans, where the groups are on opposite sides to one another or of one another. So we now know what A is. Go ahead.
Is that letter D?
Yes, that's D.
Okay.
So before on C, just to make sure it's correct, those aromatics are cis, right?
Well, okay, so that's a great question. So I want you to think about something. With a triple bond, the geometry is 180, right? So there is no cis or trans on a triple bond. Cis or trans would be with respect to these carbons right here. Their orientation around that triple bond. But if you notice, I drew them on a straight line on purpose because the angle here is 180 degrees. So there's no cis or trans on a triple bond because everything is straight. It's like a cylinder. Now you can look at the two groups and say that they're on the same side, but there's nothing that governs that because you can always rotate like around the single bond here. You can rotate around that. So they can be up, down, same side, opposites, it doesn't matter. But there's no cis or trans on the actual triple bond.
Okay, so only relates to double bonds. Okay.
Yes. That's a good question, though, and I know why you asked it, because the two groups are kind of hanging down on the same side, but that's because they're on these carbons out here. Right? They're not actually on the triple bond itself. If they were on the triple bond, it would look just like this. It will be straight because the bond angle is 180. All right, we got to stop here. I'm gonna stop recording and stuff, and we'll pick this up Friday. Remember, on Friday, we're gonna take